Okay, so my name is Gamsara, and this paper is titled Predicate Pushdown for Data Science Pipeline. It was published in SIGMOD last year, and it focuses on a well-known optimization, which is predicate pushdown, and it explores how to achieve it in data science pipelines with non-relational operators. So it's commonly believed that filter conditions must be pushed down as close to the bottom as possible to bring as many filter conditions closer to the data source, so that the irrelevant data will not be queried. So due to the separation of the storage and computing, predicate pushdown aims to push all the predicates down close to the storage node, as shown in this figure. And this reduces the computation of subsequent operators and the amount of data transmitted on the network.
That's the computation layer.
So this is the computation layer, and this is the storage layer. And then the filter used to be here in the computation, and it was pushed down before the join. So they perform the join in the computation layer, and they filter the data before they join the.
That's not a typical movement. When you apply the pushdown operation, you don't usually push down the filter predicate below the bottom storage layer.
Yes, not usually, but if we want to transfer less data to the computing layer, it's better to filter.
That only can be applied to smart storage, smart SSD, like something, intelligent storage devices.
We can see it more, I mean, it doesn't have to be a computing layer and storage layer. It can be a server and a client, and we're bringing data to the client, so we're reducing the amount of data. Okay, so for example, here, we can either load the whole table T, which we're going to select everything from T, group by month, having max revenue more than 1K or 1,000. So we can either load the whole table T and perform the group by and filter on max revenue at the server side, or we could push the filter on revenue through the group by and process it in the storage or in the server, let's say. So if we do that, we load a subset of T to the client. So when we move this to the storage, it results in less and less data to be processed. So we don't have to read the entire file or filter the data before loading it into the memory. So which can potentially accelerate query processing. So an existing DBMS system, when can predicates be pushed down? This is often decided by some rules that are implemented into the RDBMS. And for instance, for predicates involving columns from one table, they can be pushed down through inner joins, and for predicates on grouping columns, they can be pushed down through group by. But I will explain a little bit more later. So the problem with these rules and the pattern matching operators with predicates, they are far from sufficient for data science pipelines, because data science pipelines use a lot of non-relational operators, like changing maybe the data type of a certain column, or maybe dropping some tables. So very often the predicate can be pushed down through an operator or UDF, but such optimization opportunity is missed because existing rules do not cover this particular pattern. Also, an explosion of new rules would be required to handle all of the non-relational operators and the rich syntax of predicates. So making the rule-based approach a little bit harder to scale and manage.
What's the exact meaning of the pattern matching operators with the predicate?
So pattern matching means if we see a group by and then an aggregation on maximum revenue, for example, if we have this specific pattern, then we deal with it in a specific way. That's what it means. So if we have an aggregation plus group by, then the parser or the query planner will push the predicate in a certain way according to some rules that are preset.
Okay, that's the first thing. You have to identify the template structure.
So I will describe it.
Or something like that.
Yes, yes. You have to
extract. Once you find the pattern, then you can identify the predicate that can be the candidate.
Yes, or how to push it down, yes. So there's 16 rules in total that exist in current RDBMS, but anyways. So before we start a case study example, I'm going to formally define the predicate pushdown problem as follows. Given an operator OP, so OP is, for our previous example, it is an aggregation on max revenue, for example, and then a predicate F on its output. Predicate F is the filter predicate, which is having, for example, max revenue more than 1,000. So we want to search for a predicate G on the input, such as when we apply the operator and then the filter is the same as when we apply G and then the operator. So this is a filter on the output of the operator, and this is a filter on the input of the operator, pretty much. So we end up filtering the data before performing the aggregation or the group by. Okay.
So it's based on equivalence of relation in relational algebra, right?
Yes. So supposing OP is a function that filters out rows in a table based on some criteria. For example, it only selects rows where a certain column is greater than 20, and F is another filter. For example, it checks if all the values in the column are even or something like that. So when we find G that we could apply on the table T beforehand, so that applying OP after G leads to the same final result as applying F after OP. There's an example. So we start with individual operators, and then we discuss pipelines a little bit later. So in this figure, it shows the same query as earlier. It's a group by operator implemented with Pandas API with the maximum aggregation on the daily revenue. So the result of the group by goes through a filter F, which is this one, which selects rows with the maximum revenue is more than 1,000. And the output table will only include the rows for January because only January has a maximum revenue greater than 1,000, right? So when we perform OP of T on the input table, we do the group by, and then we select which is the month that has a daily revenue more than 1,000, which is the maximum revenue January is 102,000, and then the maximum of February is 400. And then we filter, means we check which one is more than 1,000 pretty much, which is only January. So we end up returning these rows. That is the result of the query. But this predicate can be pushed down, meaning there is a rule for it, which says that the pushdown is correct under maximum aggregation when the predicate on the aggregation column is on the form of column aggregation is more than a certain constant or more and equal to a certain constant. So when performing OP of GT with G being revenue is more than 1,000, what we end up doing is we perform the filter on revenue more than 1,000 before we do the group by. So if we do that, we end up with only one row, and then the group by will not be done because we only have one row, but if we had more months, and we would perform the group by. But eventually, it's going to form a filter or OP on less rows. So this is the case that is covered by the rule. So this figure shows the exact same group by, but it is with a different syntax. So the maximum aggregation here is defined as a user-defined function. And this user-defined function works like a reduce function that takes a accumulative value and then a row, and it applies it accumulatively to each row in the group. But the rule, so the above rule that was in the previous slide to push down through maximum aggregation does not recognize this opportunity or does not recognize the UDF as a maximum aggregation. So it misses the push down pretty much. So it's not defined as a rule, so it will not be pushed down pretty much, even though it's doing the same thing as the previous slide.
The main challenge with the UDF is the system cannot recognize the UDF as a proper target.
Yes. So another variation of group by operator where it counts the maximum weekend revenue, for example. So although the exact predicate can be pushed down, a more selective predicate G of weekday in 6, 7, Saturday or Sunday, and the revenue is more than 1,000 is also a correct predicate. But a new rule is needed to generate this more selective predicate that checks if the condition or if the revenue is in Saturday or Sunday. So this is also an opportunity that is missed.
So solution to this challenge is to decompose the UDF into the identifiable primitive
Components,
operation?
yes. Okay, so the final one is that if not all if conditions can be directly added to G, like this figure. So it shows an aggregation taking price times quantity. So if the revenue in the input table is null, then we can calculate the revenue by timing 200 times 6, and we get the daily revenue. So in that case, there's another UDF that's going to, if it's not null, then we take the revenue, and if it is null, then we calculate it. And this is also a missed opportunity. There is more case studies related to other operators, but they are not included in this presentation. So in this case study, we can see that even though the pushdown for maximum aggregation has been proposed as a rule before in existing RGBMS, it's far from enough for the various max-like user-defined aggregations. So with hundreds of operators and illimited UDF expressions, designing more rules to cover all the cases is simply tedious and maybe lacking. So instead, they propose a novel search and verification mechanism. It's called magic push. And magic push, given an operator with an embedded UDF and a predicate on its output, magic push will enumerate candidates or G candidates that are predicates on the operator's input, which may not necessarily be the same as F, and verifies the correctness of each candidate. So a little bit more in detail. So we start with individual operators, and then we discuss predicate pushdown in data science pipelines later. So magic push starts with enumerating all the possible predicates on the input, and then performs a bounded verification with something called SMT solver. An SMT solver is called a satisfiability modulo theory. And it's basically, it takes two equations that are symbolically executable, and it verifies if they are equal or not.
SAT solver is SMT solver?
Yeah, it's SMT solver. So they use SMT solver, which uses symbolic execution to compute the equation, and then they use it for verification because it tells us if f of OP of t is equal or equivalent to OP of G of t. Okay, so to enumerate the G candidates, they're going to start with extracting predicate components from F and from OP. So for example, from F, they will take parts that might be related to the input data. For example, from earlier, the revenue has to be more than 1,000, for example. That is a component that's related to the input. And then from OP, they extract components that is related to the UDF and the conditions. For example, if there's an if statement or a computing expression, they extract these components, and later they combine them and generate potential candidates. First of all, they test with F. If they can push down F as is, they will do that. If not, they will try to generate all possible logical and or combinations, and then they verify them from the most selective, meaning the G that will filter out the most rows from the input. So that's how they enumerate all of the G candidates. After that, they will symbolically execute a filter on the result of OP, and OP on the result of the filter candidate G, and then perform an equivalence check. So to symbolically execute, they start with a symbolic table, which is the same as the original or the schema, the table schema as an input. But before that, I'm going to explain a little bit what is symbolic execution. So in general, executing a program means executing a specific path of the program according to some specific input, right? So for example, if the function foo here is called as foo of 1, the execution starts with x equal 1 in line 1, and then it's going to execute line 2, line 3, line 4, and then line 7. And they are executed in order with a final result of I equals 1. So the symbolic execution uses symbols instead of specific input values, and they can be applied to predict the execution model of the program. So if we perform a symbolic execution without knowing the value of x, in the end, we will reach two cases, which are I equal x and x is more than 0, or I is equal minus x and x is less than 0 according to the condition that is here. So I is more than 0, then if x is more than 0, then I is equal x. And if x is less than 0, then I is minus x. So these are the two, how to say, outputs that we're going to reach in the end, or the execution paths. So this is the symbolic execution tree of this specific program. Each branch will accumulate some conditions from the instruction below, or sorry, above. And each branch condition is required for the path to be executed when formulating the value of the symbol or the end result or whatever we're looking for, execution path. So going a little bit a step further, if we want to perform a test that executes a specific code, for example, we have a case where the code in line 6, which is a equal a plus 10, we want that to be executed. So in that case, we can create a control flow graph expressing the control flow of the program, and we distinguish the destination of the branch from the code following the branch. So the destination of the branch is going to be 4 and then 6 or 12 according to whatever branch condition we have, and the code following the branch is 8 and 14. So as a result, the value that satisfies the condition a larger than 0 and smaller than 100 is the condition that is going to execute line 6 specifically. So that is in brief what symbolic execution is. Yeah.
What if you use the method push to enumerate all possible predicates that can be applied to this function and generate lots of predicate?
Yeah.
But if the predicate, the generated predicate actually constitutes the entire set, I mean that all the predicates actually have some disjunctive relation.
Yeah.
Then if you just push down all the candidate predicate down to the solid layer, then it will emit the entire set. It doesn't filter, right? It's possible.
Yeah, in the beginning when they enumerate,
extracting the predicate from the two, if else, then if you generate and combine them together using disjunctive operator, then it will actually constitute the entire set.
It does, but not all of them are correct.
Exactly.
So they use symbolic execution to test which ones are correct, means which ones are equivalent to the execution of f of O P of t. So I will explain how they do it in Magic Push right now.
Using the previous example, you generated two different predicates, right?
Yeah.
One is x equal to greater than 0, and x, what is it?
Yeah, which is this one, right? Yeah. So
you cannot use both, right?
So we see which one is the desired input for output, for example, means we define, okay, this line is going to be filtered and this line is not going to be filtered, for example. And then they have, so in the next slide, I will actually explain that. So they will have the case and the counter case, and then they will compare the executions. So I'll show you in a figure, just a second, please. So in Magic Push, they practically do something of the sort. So just some details, they add two symbols to represent values in the table. One is to handle the null values of each cell. And another one is row exist, which is basically the condition for that row to not be, how to say, filtered. So here means in the end, what is the condition that's going to result in this row being filtered? And then this is telling us if this specific value is null or not. So it makes it easier later to handle the null values. So when it comes to computing f of OP of t, of course, we know we're going to do the operator first, and then we filter on the output of the operator, right? So in that case, the outcome is an expression, because whether a row will pass a predicate f is decided by an expression. So we use row exists to indicate that. So first of all, this is the max revenue. So they compute maximum of V2, V2, and V4, V4, which are these two. They check which one is the maximum out of them. And then they have row exist, which is basically the same condition as here, but it has to be more than 1,000. So this is where they do the filtering, and this is where they do the aggregation. And this is where they do the group by, basically. So this one has to be equal to this one. So after they generate this expression, and then they make row exists, which is the condition that's going to result in a filtering or non-filtering of that specific row, they also similarly compute OP of GT. So in the beginning, this is going to be G of T, which is the filter on, the filter. And then they compute OP of G of T, and they result in a symbolic table similar to this one. And then SMT solver is going to compare between these two, conditions here, and then tell us if it's correct or not, based on the two conditions.
So suppose you have a two different predicate set that are disjunctive, okay, depending on the condition.
It's not about this. They test them one by one.
Yeah, suppose we have a two based on the condition, if some if condition.
Yeah.
This set can filter like let's say 10%, and the other one only filters 20%.
Yeah.
Then how do you deal with it?
Okay, I'll talk about that a little bit later. It's called a superset verification.
Superset.
Yeah. So okay, so we similarly, like I said, we similarly compute OP of G of T. Yeah, another one, and then.
No, please answer here. This is another question.
Okay, another question.
Question number one. Question number two is what if the function internally, UDF internally, return two different type of the column.
Returns to different type of column. They have some.
If it satisfies some condition, then it returns column A. The other one, else it returns column B. Then the function actually got two different types, right?
Yeah. So it's a it's going to diverge. They cover this case also. Yeah. Okay. So like I said, we have a symbolic input table, and then we're going to do the symbolic execution for f of OP of T and the symbolic execution of OP of G of T. And then these two symbolic tables will go to SMT solver, and it's going to test if f of OP of T is equivalent. I'm not going to say equal, but equivalent to OP of G of T. If it passes, then we return G. If it fails, then we check the next one, which is the next least, well, the less selective one, because they're ordered based on selectiveness order.
So my understanding is SMT solver is basically verifying the correctness of the candidate predicate.
Yes. Okay. So it takes two, because we said here that it's going to result in two expressions, right? So it's going to compare the expressions, because SMT solver takes two equations and tells us if they are equivalent or not. That's what it does. I don't know exactly the details of how it's done.
So it is useful to identify some bogus, useless predicate.
Yes, to verify.
Okay.
Yes. Okay. So yeah, so if once it's verified by SMT solver, it means that for every table of size 2, because here we have the symbolic table is of size 2, then the push down is correct. I will handle the full verification later, but for now, we know that SMT solver is useful for bounded verification. So if we, right now, at this point, if we want to verify a table of size 10, or symbolic table of size 10, we have to redo the verification again. Okay, so now we have an idea in general of how magic push performs a push down for a single operator. And we summarize. So the predicate search module is going to return one candidate G in the beginning, which is the most selective. And each candidate will go through an equivalence verification to check if the equation is correct or not. If it passes the equivalence verification, then it will return, stop and return. But if it will fail, then it will go to superset verification. What superset verification means? With equivalence verification means we can replace F with G. But for superset verification, it means that G will filter a lot of the rows or some of the rows, but we still need F to filter on the output of G of OP of T. But still, since G is the most selective out of the generated or the enumerated candidates, we still return G, but we don't get another one that is less selective. So that's what the superset verification. So in this case, F is gonna filter 20 rows, but G is going to filter, let's say, 10 rows. Okay, good enough. But later we're going to filter again, but still we're transporting less data over the network. Okay, so if it passes both, then it will return the candidate G but if it doesn't pass both, then it will generate another one that is less selective. For data science pipelines, each operator has one input and one output, right? Because it's, how to say, a series of operations that are going to be done on the data. So in that case, Magic Push will decide the push down for each operator from the last operator to the first. So it starts from here and then it goes to the start of the pipeline. So in the beginning, it finds G2. It will find G2 from, giving OP2 and the filter F, and it's going to produce DF2, which DF2 is the output of operator 1. And then it will push G2 through OP1 and obtain G1, which is the filter on the output of the table DF1. A question was asked to me yesterday in rehearsal, what if we don't find a G? Then the input here is going to be the same here, if we don't find a G on this operator. Okay, so we said earlier that the advantage of SMT solver is using it for verification, and it can handle almost any operator or UDF as long as it is symbolically executed, or it can be symbolically executed. But the problem is that it is bounded. So we only know that the pushdown is correct for a table of a certain size that we used. And if we want to verify with a different size table, then we want to prove its correctness again. That's why they propose finding and providing a precondition P leading to small model property. And it means that as long as F and OP and G satisfy a certain precondition, a bounded verification can be extended to a full verification of any table of any size. So if we verify P and the pushdown equation on the symbolic table of 2 rows, we can know that the pushdown is correct for a table of any row. So a little bit more on P. So basically, P can lead to an inductive proof. It's different for each operator, but looking at selection, no precondition is needed because it handles row-to-row operation. It's a single row operation. So in that case, the inductive proof looks like this. Assuming the pushdown holds on any table whose size is not greater than n, we can prove that it holds for a table of size n plus 1. And they formulate this table T prime as T union 1 row, right? And following the inductive proof, we can prove that it is equivalent to the selection of a smaller table. In that case, any verification on a table of size n can be executed on, or so can be correct for any table of size n plus 1, which makes it correct for any table of any size. So moving a little bit to aggregation, with aggregation, it's a little bit more complicated. So it's summarized a little bit in a high level. So it includes 3 preconditions. One is that the aggregation is associative, commutative, and can be reduced to a smaller table. It means the order of the columns does not matter if we are doing the group by. So when the aggregation cannot pass F, then there's no subset that can pass F. For example, in maximum aggregation, when the maximum of a certain, how to say, revenue, for example, is less than 1,000, any subset of this group is still smaller than 1,000. The third precondition is that a subset of T of G not passing the filter G has no effect on the aggregation. What it means is that if the maximum of a group is larger than 1,000, like our example, we can remove any row that is smaller than the maximum and the result will still be the same, or the result of the aggregation will still be the same. So max revenue will still be the same if we remove all of the rows that don't have, or they don't satisfy, or that are less than the maximum revenue. So with these rules, we can say that the aggregation passes or is correct for any table of any size. So they make a list of preconditions P for 7 types of core operators, representing these are 120 pandas APIs. They summarize them in 7 categories. We said the row to row, and then aggregate, and they create preconditions for other, categories also. Okay, so the limitations of this project is that Their unhandled operators are if we have a row in the output that relies on rows or on all rows from the input, for example, transpose, they don't cover this case. If the operator is position sensitive, means shift, for example, then it's also an unhandled operator. Okay, so moving to evaluation. So magic push is implemented in Python with the SMT solver called Z3. And the input is the pipeline in Pandas API with UDFs in Python syntax. The output is an optimized pipeline in Python, and it handles 120 Pandas API. So the baseline is the 16 rules that are collected from previous work or RDBMS, and they contain a lot of operators. So they can optimize all TPCH queries. So the baseline can optimize all the TPCH query, and it pushes the predicates close to the source table as long as it has a rule. Also, when they run magic push with TPCH, it discovers all the pushdowns found by the baseline. So it covers all of the 16 rules that are already explicitly stated. So for real-world data pipelines, they sample 200 Jupyter notebooks from GitHub that use Pandas library to process data. And out of 200, 95 cannot be optimized, means there's no opportunity for pushdown. Among the 105 that are remaining, the baseline can optimize 74, and magic push can optimize all of the 105 remaining. So magic push returns a more selective predicate in 42 pipeline, means it filters more, it ends up filtering more rows compared to the proposed rules. So the figure here, the first one, shows the amount of data that is reduced by the pushed predicate measured in row count. And it's ordered by the most improvement to the least improvement. So we said earlier that magic push is able to push down predicates to the pipeline input of 105 pipelines, while the baseline does only 74. So in 42 pipelines, which are these ones, magic push reduces more data than the pipeline by 42% on average, and in some cases by 99%. So this figure, the next one, it shows the end-to-end performance gain on both the original and the scaled data. So on the 42 pipelines where magic push can reduce more data, it achieves better performance gain on 38 pipelines out of 42. So there is ones where the baseline performs better. So I'm going to explain it, which are these three pipelines. So for magic push, the running time takes mostly less than 1 second, but there are only 3 pipelines that it takes longer time to optimize, which are complicated UDFs and large symbolic tables. In case where they have to perform an unpivot on a very wide table, it's gonna take the columns and turn them into rows. That takes a very long time. Also, when there's a very complicated IDFs with many branch conditions, it also takes a long time to optimize. So yeah, magic push. It performs predicate pushdown optimization. It has a high coverage on relational and non-relational operators and operators with UDFs embedded. The precondition P on 7 core operator types helps us symbolically verify the query on a constant size table using SMT solver and guarantees the full verification. And it's better at reducing the amount of table or the amount of data compared to the baseline in general.